Well, hello, I'm Eric, and I'm back to talk to you about some calculus ideas. And disclaimer, first of all, health sciences is not my area. My training is mathematics. I earn a living teaching mathematics, and it's rare, but occasionally it happens that I become interested in applied mathematics. And so I came across interesting concept back in 2002 when SARS was one of the big stories in the news. And I find that today with COVID-19 and all the impact on economics and health and people's confidence in our systems, you know, it's sort of interesting that a simple model, a mathematical model, can help explain and help predict what it is that we might be facing here. Now, I'm not here to make any kind of predictions or prescriptions, just to look at the mathematics behind a simple model and perhaps to look at some of the calculus involved with it. The model is called the SIR model. S stands for susceptible, I for infected, and R for removed. And the idea behind the model is that when a virus is spreading through a community, at any point in time, you can divide this community into three groups. Those who are susceptible, those who are infected, and those who are removed. There is no sitting on the fence here. You are either infected or you're not. So you cannot belong to two of these groups. That's one of the assumptions. Another assumption is that members of any one group are fairly uniform. And again, you know, these assumptions may or may not hold when compared with reality. So there are coefficients that determine the rates of transfer between the groups, and we'll talk about what those coefficients are. Then as far as movement goes, okay, it's all from left to right. In other words, a susceptible person who is defined to be not immune to the virus or the disease because they've, you know, not been afflicted with it previously, they're capable of catching it, and that's all we know about them. Okay, the infected people, who are they? There are people who have and carry and are able to transmit the virus, so they are contagious, and they may be symptomatic or not. They may have just, you know, a sort of a mild stuffiness in their nose, or they may be near, you know, death's bed. So finally, we have the removed group. Now that word is, you know, a little. I've also heard it called the recovered group, but neither one of these words is very good in my opinion. I think they could come up with something better. Basically, who is in the removed group are people who have been infected and no longer are. And so you can imagine there's pretty much only two reasons that you would move out of the infected group into the removed group. Either you successfully fought the virus, you've recovered, you're feeling pretty good, and most importantly, you're no longer contagious. Or you had a bad time with it, it took you out. Okay? Not nice, but it happens. So when you get to the removed group, it doesn't mean they're going to put you out in the woods for half a year. It doesn't mean you're removed from society. You are removed essentially from the model in the sense that you cannot infect anybody and you cannot be infected. So you're not part of that calculation anymore. So that's what the removed group is. So one more time, you can move from here to here and you can move from here to here, but nobody moves back in this direction. Those are some of the assumptions. Okay, now we're going to talk about the rates of change. First of all, let's talk about the transfer from the susceptible group. Where do they go? They go into the infected group. And it's not a constant rate. So today, if 10 people move from not being sick to being sick, that doesn't mean tomorrow that it will be 10. The rate turns to vary quite a bit. And the general pattern is, in the beginning, there is a slow transfer from susceptible to infected. and also late in the epidemic, there's a slow transfer. But in the middle, the transfer is quite high. Now, the assumption of the model says people are moved out of the susceptible group at a rate proportional to the product of S and I. So S is how many people are susceptible, it's a number, counting people, and I is how many people are infected. These being variables, this statement is saying that, yeah, the rate of transfer out of this group will be a variable. And to wrap your mind around how that works, I thought we'd do a simple example. We take the removed group out, just ignore it for a minute, I know you shouldn't, but we would just look at the two groups, the S group and the I group, and throw some numbers up there to give you a feel for how all this might work. So, let's suppose there's some closed community of only 40 people, and right now 39 of them are susceptible, and one of them is infected. Okay. What does that mean? The maximum number of possibilities, or of possible infections today is 39, because this one person can infect any one of these 39 people. That's a maximum number. And this statement says that some percentage of that maximum number of possible infections is going to occur today. And I'm just going to make up a ratio here and say that it's 5%. Probably way too high. So the idea would be that if you had 5%, or 0.05 is decimal, times the product SI, you would be able to compute the rate of change of transfer from susceptible people to infected people. So let's compute the product SI. That's 39 times 1 is 39. Again, that means there's 39 possible transmissions today. Let's take 5% of that. Well, 5% of 39, I'm going to approximate a lot of these calculations. 5% of 39 is approximately 5% of 40, and that turns out to be 2 people. Okay, what does that mean? That's 2 people per day moving from this group into that group. So, let's move those people. 39 minus 2, we're down to 37 susceptible people. We have this guy who was infected yesterday, he's still infected, and we've increased that by 2, so now you have 3 infected people. Next day, we have 3 people who are infected and 37 who are not. Each one of these 3 people has the possibility of infecting 37 others. It doesn't mean they will all get infected. It actually ups the odds a little bit, because each of these people is 3 times as likely to get infected as they were on the first day, subject to some ratio like 5%. So if I multiply 3 times 37, I get 111. And the units here, if you're keeping track, would be people squared. So basically, there's a possibility of 111 different transmissions on this day. And some fraction of that, 5%, is going to be how many people get infected. So 5% of 111, somewhere around 5.5 or 6. I'm just going to go with 5. Well, we're losing our susceptible people. We had 37. We're going to lose 5 today. Notice that's more than yesterday. 37 minus 5 is 32. We have 5 new infected people. They go into this group, so now we're up to 8. Okay, we still have a high number of susceptible people, but now we have a lot of people capable of infecting. 8 times 32 is 256. That's the total number of possible transmissions on this day. We have to take 5% of that. So that's going to be about 12 people. Roughly 12 or 13. As you can see, these are rates, people per day, moving out of here and into here, and this rate is growing. You see on the news how they talk about the number of people in the infected population is growing exponentially, and I think they say in New York right now it's doubling every 2 days. We are in the early part of the model. The part where this group is still large but shrinking, and this group is growing rapidly. And the bigger this gets, up to a point, the faster it grows. It does look like exponential growth in the beginning of the model. So, we have 12 people moving out of susceptible and into affected. Well, 32 minus 12 is 20. And 8 plus 12, right, because they're going from here to here, is 20. Now look at this. This is just the perfect storm. 20 infected, 20 susceptible. Each of these 20 susceptible people will possibly contact 20 infected people. It really drives up the number of infections on this day. So 20 times 20 is 400. 5% of 400 is 20. And that basically wipes out the susceptible group. Doesn't mean they're all deceased, it just means they're all transferring. So the next numbers would be 0 and 40. And then as you can see, what's the product of 0 and 40? Well, there's nobody left to get sick. So there are no possibilities for transmission anymore, and all of a sudden this number takes a nosedive. And that's the end of the model. Now, we didn't take into account the transfer from the infected over to the removed group, because that's also happening. This infected group is kind of complicated. There's a transfer into it and a transfer out of it, and these things are happening simultaneously. And so, well, we'll talk more about that in a minute. Let's go to this next assumption. People move out of the infected group. Before I move on, let me just summarize what you're supposed to learn here. Okay. When this product is as large as possible, you'll get the highest transfer out of the susceptible group. What does that mean? Lots of people every day, new people getting sick. Okay? So, you don't see that in the beginning. There's not that many people here to infect. And also, later you don't see that because there's almost nobody left to get sick. The actual model will slow down before you get to that extreme that I just talked about there, right at the end of that table. Let's take a look at this next assumption. People move out of the infected group at a rate proportional with the size of the infected group, which is determined by the average term of the illness. Okay. That's a pretty big assumption, but it turns out as long as you're talking about very large numbers of people, this is probably true. So pretend for a minute that the period, I'll call it, or the term T for this illness is 14 days. And just because 14 goes nicely into 28, let's pretend that we have 28 infected people, represented by the length of this rectangle. 28 infected people. Well, they didn't all get sick today. Some of them are newly infected, and some of them have been infected for a week or more. And so the assumption of the model at this point is to say, well, there are 2 people right here who just got the illness today. Right next to, if you order them in terms of how long they've been afflicted, there are 2 people right next to them who got the illness yesterday. There are 2 people next to them who got the illness the day before yesterday. Likewise, way down at this end, you have 2 people who are on the 12th day of their illness, 2 people who are on the 13th day of their illness, and 2 people who are on the very last day of their illness and ready to do what? That's right. They're ready to transfer out of here into the removed group. So that's 2 people per day. All right, so in general, how do you calculate that? You take the number of infected people right now, whatever it happens to be, and you divide it by the term of the illness. It'd be that 14 days, 20 days, whatever it is. So, let's write down some differential equations here. Well, let's get to the final group here, and then we'll write some differential equations. So we have an susceptible group to start with, and we know that they transfer into the infected group. At what rate did we say? Well, it's some constant k times the product of S and I. And I went through a very concrete example of that where we looked at 40 people and we saw how the numbers changed. We used a k value of 5%. So that is the rate of change out of S. But because S is getting smaller, in calculus we would write ds dt equals negative k si. The rate of change in the susceptible population per day, people per day, is proportional to, it's negative, and it's proportional to the product of the size of these 2 groups. Okay. Now, we have a transfer from infected to removed. And that's the only rate that matters for the removed group. So what is that? Okay, we just talked about that. The rate of change of the removed group is positive because this is always growing, and it's proportional to how big the infected group is, and the constant proportionality has to do with the term of the illness. So it's 1 over t times the size of the infected group. An example we had a minute ago, we had 28 infected people, we had a term of 14 days, we divided those and we got 2 people per day moving into this group. Well, what about the infected group? What is its rate of change? This tends to make it grow, and this tends to make the infected group decrease. They're competing. Think of it as you've got a bucket of water, you're filling it from the faucet, but it has a hole in the bottom. Is the water in the bucket getting deeper or not? Well, it just really depends on the comparison between the added water and the leaking water. The same thing is going on with this group. So here is the differential equation for the, or not the differential equation, excuse me, let's just call it the rate of change of the infected group in people per day is this without the negative, because these people subtracted here are added there. So it's k times si and then minus the rate of change at which people are added to the removed group. Okay? Why are these equations important? They're not. If you don't plan to build a model, if you don't want to study these things, if you don't have a calculus background and don't intend to someday, then that's okay. I'm doing this largely for people who are interested in mathematics, maybe have a little calculus in their background, and are interested in how math can help us solve real-life problems. You don't have to know that much, though. These get used in what are called Euler equations to make a model that I'm going to show you right now. I've been tinkering with this model for a couple of days. It's a spreadsheet. I made it on Microsoft Excel. You could certainly make one on Google Sheets, and let me show you how it works. Just before I show you, remember the K value that I talked about? I gave you a specific example of 5%. It's the coefficient that's used on the product of the S and the I, the susceptible and the infected, and it determines the rate of flow out of the susceptible group and into the infected group. That K value turns out to be probably the most important part of the model, as you soon shall see. We want to know what effect the K value has on the maximum number of infected people at a given time. This is the one they're always talking about on the news when they talk about flattening the curve. Yeah. What effect does K have on the number of people who at some point become infected? You know, like it turns out sometimes not everybody gets sick. What about the maximum rate of new daily infections? What effect does K have on that? What effect does K have on the number of deceased people? I mean, some people are going to die. Does K have an effect on that? What about the number of days before the model stabilizes? Turns out K has an effect on all these things, and I'll do my best to answer each one of these questions for a variety of K values. Then we might want to know, what about the term of illness? Is it 14 days or 21 days, and what effect does that have on the model? Will everybody get sick? If there's a way to make an organized response to suppress this transmissivity rate, K, when should we do that? And let's try to answer those questions now. Okay, spreadsheet. Susceptible people, infected people, removed and deceased. I'm going to assume you can't really see that stuff very well. I have this set up for a population of 200 people. Now you could easily scale that to 200,000, 200 million, whatever you want. Down here I have time, and because I have the Euler step set to 1 day, these are actual days down here, if you can read them. So this one, for example, says 81, that's 81 days. I have 4 graphs up here. The red graph is the number of inflicted or infected people. Remember, they're contagious, they can spread. It spikes very early in the model and then decreases. This is the one everybody's so worried and concerned about, as they should be, because if it gets up to something that's approaching, I don't know, half of our population, there's no way our medical systems are going to be able to handle that many people all at once. When they talk about flattening the curve, that's the curve right there. That's the one they want to keep down. And the good news is there's ways to do that. Okay, what else do we have? The blue, susceptible population, just drops very, very rapidly, as you can see. The green curve would be the removed group, including all people who successfully fought off the virus and survived, as well as the people who didn't. And then finally, I have a purple curve down here for those who are deceased. And we can scroll down and look at all the numbers to see how things are going. Right now, with a K value of 0.001, the model is rather alarming. Mostly because of how high this population of infected people gets relative to the total population. We're going to go up here now and play around with the infection rate and the infection term. First, let's go with a much smaller infection rate. Let's cut it in half. So instead of 1/1000th, I have 5/10,000ths. That is dramatic in many different ways. It's not just the number of inflicted people who dropped from around 100 to sub 50. Okay, that's good news for our our health facilities and our hospitals and doctors and so forth. But what's also kind of interesting is the number of susceptible people does not go to 0. These are people who never got sick, and they won't, because this thing is stabilized. Yeah, now it did take about a couple hundred days for that to happen. Well, why is it, though, that there are people who don't get sick at all? And the answer is, you don't get sick if there's no infected people around to make you sick. That infected population dwindles to almost 0, and why is that? Well, remember, there's people moving into the infected group and people moving out. If people are moving out of the infected group faster than they're coming in, that's when this population starts to dwindle. And if it gets close enough to 0, there are no new infections. So a lower rate of transmission from the susceptible into the infected, a lower rate there is got lots of good news, including, well, here's another one. When we talk about mortality rates, I've got this set to 3%. That's one of the numbers they're throwing around in the news lately. The mortality rate is not a fraction of the total population. It's a fraction of the ultimate number of people in the removed group. So here I've got the removed group going only up to about, 170. 3% of 170 is how high this purple line climbs right here, this purple curve. That's your mortality rate. Not your rate, but your actual number of people who have died. 3% of something smaller than 200, that's saving lives. Let's go back to the original. Yes, with a transmission rate of 0.001, almost everybody ended up going into the removed group. That's 200 people roughly. 3% of 200 is 6 deaths. What if we could get that removed group down to 100? Well, then we would cut the number of deaths in half. And by the way, if 6 deaths doesn't sound like much, remember this is just 200 people. If you're talking about 200 million people, you're talking about 6 million deaths, and that's a frightening thing to think about. So I'm going to take this rate and try to cut it so that it's 25%. Or 1/4 as large as the original one. And look at that. Nothing sort of an astonishing result if we were able to do this, as a society. If we followed some of the rules that are being, of course, they're inconvenient. School closures, restaurants closed, so forth. Yes, they're temporarily really horrible, but I think we can do this. And the model would suggest that it's a very good idea. How many deaths do you get in this situation? Well, the people in the removed group are around 50. 3% of 50 is about 1.5. So only 1.5 people die. That's pretty good. Let's restore the model now to the original transmission rate, which is alarmingly high. What about the infection term of 21 days? So remember what that affects. How quickly people move out of the infected group and into the removed group. Well, we don't have any control over that. It is what it is. It's a function of how potent the virus is to begin with, but also how healthy the society is that's infected, average age, things like that. That determines how long the disease is going to last for the average person. Nevertheless, this is a mathematical model, and there's no price to pay to go and tweak that number. I'm going to shorten the term of the illness to 14 days, and you'll get to see how the model responds. Okay, there was a significant difference there. Because I changed this to 14, people are moving out of that infected group faster, which tends to pull down the spike, and it tends to make the model run shorter. We get through it faster. That's pretty logical stuff, I think, isn't it? Anyway, back to the original status. Okay, to answer one of the last questions that was on that list, and if you have further questions, you can post them up and I'll try to get to them. I went ahead, I like these spreadsheet things, because I did not grow up with them, and I taught myself how to do them, and boy, I think they're fun. I went ahead and modified this so that we can look at two things. One, I can reduce the infection, where to go? Up here. I can reduce the transmissivity rate by some percentage factor. I've got it set to 1 now, which means nothing's been done. And I can do that at any point in the model, drastically to change it, depending on what I do and how soon I do it. In other words, this model will run up until some day, like let's suppose we say, okay, this virus, the affected group is growing exponentially, it's doubling every 2 days, oh my God, we have to do something about this. But let's suppose we waited 4 weeks to do something about it. 28 days. What would happen if on the 28th day, okay, not in the beginning, not up here, but on the 28th day, what would happen if we suddenly took all these drastic measures to, from that point forward, cut the K value? Cut the K value by 50%, okay? Something kind of strange happens. That curve that looks sort of like a bell took a very, very sharp reversal in direction. Other than that, the model didn't change all that much. So 28 days in, you're a little late to be working on that, but you did cut it in half from that point forward. What if 28 days into this you can cut it by, instead of 50%, what if you can cut the transmission rate by 75%? Well, that would look like this. Again, a massive reversal in direction, and certainly some good things happening. The number in the recovered group, or removed group, is not up at 200. It's more down like around 160. So you won't get quite as many deaths because 3% of 160 is smaller than 3% of 200. Also, the people who are susceptible do not go to 0. That means a large number of people, 40 in this case, didn't get sick at all, which is a nice thought. But I guess the point I'm trying to make here is 28 days into this is a long time to wait. A long time to wait. So, okay, this is doing nothing. Let's try this instead. What if we did something at 21 days and we're able to cut the rate of transmission in half? There's an interesting looking curve. So 3 weeks into this, we cut the transmission from 0.001 to 0.0005, 5/10,000ths. And as we can see, that the total number of infected people did take quite the nosedive. If I can do the same thing but at 25%, this is what we get here. So 75% reduction in transmission rate. Pretty good results. If I set these back to their original values, I think you would see this number of infected people had this really big spike up here. I don't know if you call this flattening the curve or just, chopping it off. But that's the kind of thing you can expect if you don't lower the transmission rate initially, but you wait 3 weeks. And what about if you had done it 2 weeks in? So set this to 14 days. Actually, let's compare the original, because I don't know that we remember what that looked like. So originally, this is what it looked like. Transmissivity rate of 0.001. Very high spike in the number of infected, reaching a maximum of somewhere around 80 relative to 200. If that's 200 million, that's 80 million. Bad stuff, bad stuff. But what if 14 days in, we took drastic measures to cut the infection rate by 75%? 14 days in. So you change this value to 14 J's, change this to 0.25 because that's a reduction of 75%. And look at that. Look at that. There is your maximum number of infected people. Maybe that would be more manageable for our medical personnel. What about deaths? Well, now you have 3% of sub 100, that's about 3 deaths, compared to 3% of 200, which would have been about 6. Basically, you cut the death rate in half. So, what do we learn from this? I don't know. Again, I don't work in health sciences. I know a little bit about mathematics and modeling. The lesson I learned is you need to do something drastic and you need to do it early. And hopefully that's what our wise leaders are doing for us now. Okay, I think I've been a little long-winded, so I'm not going to go through how I created this spreadsheet. If I get enough response to this and people want to see how to do it, I will. I will not make any more videos for the next 2 weeks, though, because I'm in the United States. I'm up in the northwest corner near Seattle, and our governor has issued some kind of a, stay in your house order. And so I'm not going to be allowed to come to this facility and make these videos for a couple of weeks. So anyway, my name's Eric. Hope you enjoyed this. Maybe you learned something. Have a good day.